for these practice problems, we're looking at similar triangle properties. So two things you want to remember about similar triangles. So similar triangles means two things: congruent angles and proportional sides. So when we're looking at these problems, if we know that the triangles are similar, it means that the sides are proportional, so we can set up proportions, and the angles are congruent. So for number one, we're given that the two triangles are similar. It tells us the measure of angle C and it tells us the measure of angle G. It says determine the value of X. So if the triangles are similar, that means that the angles are congruent. These have to be equal to each other. So since they have to be equal, I just set them equal themselves. So 4x plus 30 equals 5x plus 10. Subtract 4x. I'm going to move the 10 over to the other side. So those cancel, so I get 20 equals x. And that's all it wants us to do, is find the value of x. Number two, again, says that the triangles are similar, so that means congruent angles, proportional sides. And this time they're giving us the side lengths here. So they give us all of these different side lengths. They want us to find the value of, or the length of AB. So I know that the sides are proportional. So the sides that correspond, I'm going to put them together. So it's going to be 7x over 7. And then 4 and x correspond. So I'm going to put 4 up top because that came from triangle number 1. And then from triangle number 2 came x. So I set up my proportion. And then from here, cross multiply. So we get 7x squared equals 28. Divide both sides by 7 to get x by itself. So we get x squared equals 4. Square root both sides. So we get x equals plus or minus 2, but we reject the negative. So we're just going to keep x equals 2. And remember, the answer is not what is x, it's what is the length of AB. So notice that 2 is one of the choices. They always do that, where they'll put your answer, your partial answer in there. But if we're trying to find the measure of AB, it means we need to plug back in. So it's going to be 7 times x, which is 2, so we get 14. So your answer should be choice number 3. The next question is just a property question. So remember, whenever we have similar triangles, we know that the sides are proportional and the angles are equal. So this is telling us the ratio of the sides. So the ratio of the sides will always be the same for any other side. So in this case, BC and EF, well, BC and EF are another set of sides. So those are going to be in the same ratio. So that's got to be true. Angles. Angles are never going to be in a ratio. They're always going to be congruent. So this is actually the statement that's not true, because angles are congruent in similar triangles. So they're not in a ratio, they're congruent to each other. Now, the area and the perimeter, I just want to talk about that. The perimeter, if you remember, the ratio of the perimeters equals the ratio of the sides. So this one's definitely got to be equal. But for area, it's the ratio of the sides squared equals the ratio of the area. So if I square 3, I get 9. If I square 2, I get 4. So the ratio of these sides squared would give me the ratio of the areas. So that's actually why that's true. So for this one, in order to make it true, you actually have to square the ratio of the sides. So that's the choice that probably most people would pick because it's a different number, but it's actually true because you always square the side ratios to make it equal to the area. So that one is true. The next example here is asking us to determine if these two triangles are similar, and it gives us the side lengths. So I'm going to go ahead and sketch this first triangle. So we have 6, 8, and 11. So 6, 8, and 11. And then a second triangle has 18, 16, and 22. I'm going to draw it so that the corresponding sides, so the smallest side would correspond to 16. And then the medium side would be 18, and then 22. So if I want to see if these are similar, that would mean that I have to use one of the methods to be able to prove it. So that means I'd have to be able to use angle-angle similarity, side-side-side similarity, or side angle side similarity. You could also show all sides are proportional and all angles are congruent, but if you look, I don't have any information about the angles. So that means what I need to do is I need to show all three sets of sides are proportional. Otherwise, these triangles aren't similar. So what I'm going to do is I'm going to compare each of the sides. So 6 to 16. So if I actually take that, 6 over 16, and reduce it, so divide the top and bottom by 2, I get 3 over 8. Then if I take the next set of sides, 8 and 18, and you reduce these, so divide both by 2, you get 4 over 9. So right there, I know that these aren't similar because the ratio of the sides are not the same, which means the sides are not proportional. So I'm going to say the triangles are not similar because the ratios of the sides are not equal, meaning they're not proportional. And keep in mind, you don't have to show that third set of sides, but this would hold true for the third set because if you actually compare the 11 to the 22, you're going to get 1/2, which also doesn't equal any of these sides. So none of the ratios are equal, which is why the sides aren't proportional. So if ratios aren't equal, that means that they're not proportional, which means they're not similar. So if we look at the next example here, this is called the side splitter theorem. So whenever you have basically a picture like this where you have a smaller triangle inside of a larger triangle and you have these parallel lines, the small triangle here has to be similar to the large triangle. And what that allows us to do, since the triangles are similar, it allows us to set up proportions. The side splitter theorem says that this small piece over this small piece is equal to this part over this part. So it's saying that this side splits the entire side proportionally. So you could set up a proportion that way. I like to think of it in terms of similar triangles because that way it'll always work when depending on what's labeled. So I'm going to use similar triangles. So these triangles are similar. Whenever you see this picture, we know that. Whenever you see the parallel lines here. So I'm going to compare when I set up my proportion, I'm going to do the small triangle to the big triangle. So the small triangle side, I have a 4. That's going to correspond to this entire side, which is going to be 12 of the large triangle. And that's going to be equal to this small triangle side here, which if you look, the whole thing is x, and then this part is 14. So this little piece is going to be x minus 14, the big part minus the 14. So that small piece will be x minus 14. And then the large side will be x. And then since we have a proportion, we cross multiply. And remember, I knew to set up this proportion because the triangles are similar. So knowing similarity really helps here. Make sure that x minus 14 gets in parentheses. So it's going to be 4x equals 12 times x minus 14. X minus 14 is in parentheses so you can distribute. So we get 4x equals 12x minus 168. Subtract the 12x, we get negative 8x equals negative 168. It's good that we have negatives on both sides so that when we divide both sides by negative 8, it becomes positive and we get positive 21 for that. And that's it for that one because you don't have, it just says find x. Number 6, same thing, find x. Again, you should recognize this as the triangles are similar because we have, again, that side splitter theorem. We have this side is parallel to this side, so the small triangle here is similar to the large triangle. So if I'm trying to find x, I want to set up a proportion. So again, I'm going to compare the small triangle to the big triangle. And these have occurred, these types of questions, there's at least been one on the last Common Core exams, the last 3 Common Core exams. So that's why I have several examples in here. So the small triangle, let's say, is x. The large triangle side is 15 then. Then if I look at this side, it's 4 compared to 12. Cross multiply this, so you get 12x equals 60. Divide both sides by 12, we get x equals 5. So you always want to look for similar triangles. So in these next couple examples, it's not the side splitter theorem, but these are still situations where you have similar triangles. So here's how I know that. As soon as I see a smaller triangle inside a larger triangle, I'm looking for either those parallel lines, which would prove that you have congruent corresponding angles. In this case, in both of these cases, parallel lines, these corresponding angles are congruent, as well as reflexive property, which is why the small triangle is similar to the big triangle by angle-angle similarity. Same thing is going to happen with this picture. Since we have reflexive property for angle C, it's shared between both the small triangle and the large triangle. And we also have these right angles here. That means by angle-angle similarity, the two triangles are similar. So again, triangles are similar by angle-angle similarity. So that means we can set up proportions. So I'm going to do it exactly like the last problem, where I'm going to compare the small triangle to the big triangle. And when you set this up, the small triangle side that we're going to use, well, we definitely want to use the 12 and the 24 because those correspond. So it's going to be 12 over 24. And then if you look at what we're trying to find AB, so I'm going to put an X there, which means I don't want to use the 13, I want to use the 5 because the 5 and the X correspond. So it's the 5 of the small triangle corresponds to X of the large triangle. Then we're going to cross multiply here. So we have 12x equals 5 times 24, which is 120. Divide both sides by 12, we get x equals 10. So again, just knowing I can do that because we had the similar triangles. So all of these triangles so far have been similar by angle-angle similarity, these last 3 examples. Number 8, we look at this picture and hopefully you're thinking, okay, the triangles are similar. I know the two triangles are similar because I have vertical angles. I also have the Z shape here. So whenever you have the Z shape, you have those alternate interior angles, and because the lines are parallel, those alternate interior angles are congruent. So what I'm going to do is, since the two triangles are similar, to solve for x, I'm going to set up a proportion. So I'm going to just write here, triangles are similar by angle-angle. So we're going to set up a proportion. Now keep in mind too, I know that angle E and angle A are also congruent because those are alternate interior angles as well, but I only need 2 sets, so that's why I stopped once I saw the 2 sets. So when I set up my proportion, for this one, I'll call this triangle 1, this will be triangle 2, so I'm going to compare triangle 1 to triangle 2. So triangle 1, I have side 3. So side 3. That's actually going to correspond to the 6, because this is almost like a twisted picture in a way. If you were to, you'd have to like reflect it and then turn it in order to get it to match up. The reason why I know that is because D and B correspond. So 3 and 6, they both are on those sides. So that's why 3 and 6 correspond. And then 5.2 of triangle 1 corresponds to X on triangle 2. So then we cross multiply. So we get 3x equals 31.2. Divide both sides by 3, and you get x equals 10.4. Example number 9 here is asking us to determine if the triangles are similar. So again, if you're trying to decide if they're similar, that means you need to identify them as similar by angle-angle similarity, side-side-side similarity, or side-angle-side similarity. And remember, the angles are congruent, the sides are proportional. So if we look at what they give us, so they say AB is 4, BC is 12, DE is 3, EF is 9, and they tell us that these angles are congruent. So right away, I think I'm going to be using side angle side similarity. The reason why I think that is because if you look, they give us two sets of sides, congruent angles, and two more sets of sides. So this is what I'm going to use to try to see if these are similar. So what that means is if they're similar, the corresponding sides have to be proportional. Now the sides that correspond are going to be AB and DE because those are both at the bottom of those congruent angles there. So I'm going to compare side AB to DE. And remember, if you're not sure which ones correspond, if you look at the order here in the statement, A, B, and D, E, those are both first, so those correspond. So when I compare those, so 4 to 3, that doesn't reduce, so I just leave it. So then I'm going to compare the other two sides, so BC to EF. And again, if you weren't sure if those correspond, you can look right here. BC and EF are in the same order. So BC is 12. Compare that to the 9. Well, that would reduce. If you divide the top and bottom by 3, it would reduce to 4 over 3. So this right here tells us that the sides are proportional. So since the sides are proportional and the included angle is congruent, that would mean that the triangles are similar. So therefore, I can say, therefore, triangle ABC is similar to triangle DEF by side angle side similarity, because the two sets of sides are proportional and the angle between them is congruent. Example number 10 is talking about a dilation. So whenever we have a dilation, that again means that we have similar triangles or similar figures. So basically we're starting with triangle ABC. So I'm just going to sketch that. And it's dilated by a scale factor of 5. So that means A prime, B prime, C prime is going to be 5 times larger. And it wants to know which statement is true about A prime, B prime, C prime. So we know that this was times 5 from the dilation. So first thing you can get rid of is choice 3 and choice 4. Because if you look, those talk about the angles, and they're talking about the angles not being equal. And if you remember, similar triangles or similar figures and dilated figures will always have equal angles. So I know that one angle is not 5 times the other. So then the question becomes, is it choice 1 or is it choice 2? So the wording of it is a little bit different for each of them. So what I would think of is, let's think of one side at a time. So if we focus on AB to A prime, B prime, you just have to ask yourself, what's the equation between them? So really, if you think about it, they took side AB, you multiply that length by 5, and that's going to equal A prime, B prime. That's what this is saying. The length of this times 5 equals the longer length. That is not what number 1 is saying. Number 1 is saying the opposite of this. So if you were to get AB by itself, which is what number 1 has, that means it would be A prime B prime divided by 5. So that's not true. If you look at number 2, it's basically the same thing as what I have. The only difference is instead of AB and A prime B prime, it's B, C, and B prime C prime. Same concept though. If I go from BC, I would have to do BC times 5 to equal B prime C prime. So that's why that's the correct answer. And for the last example here, we're talking about a tree that's casting a shadow that's 20 feet long. So let me draw that picture. So I have a tree. It's casting a shadow that's 20 feet long. Next thing it says is Jake stands at a distance of 12 feet from the base of the tree. So that means that Jake, from the base of the tree, is 12 feet from the base. So let's say he's about here. So that's 12 feet. So this whole thing was 20. So that means this remaining piece is going to be 8 feet. 20 minus 12 gives me 8. And then it says, such that the end of Jake's shadow meets the end of the trees. So that's how I knew. So since he's 12 feet from the tree, his shadow then is right here, is going to meet the tree. So that's why I know this distance is going to be 8, and that's actually representing the length of his shadow. If Jake is 6 feet tall, so he's 6 feet, determine and state the height of the tree. So I'm going to put H for height. So now, since we're talking about a shadow problem, basically what you want to think about here is, okay, you have the sun, and it's casting down, and it's creating these shadows, which really means that you're creating these triangles. So one triangle is going through Jake's head, or it's hitting the top of his head. So basically, here's one triangle, and it's going to be a right triangle. And then the other triangle is going to be the triangle that goes from the top of the tree down. So here's the sun rays creating that shadow, and then here's the length of the shadow. So these two triangles will always be similar, and the reason for that is because we have perpendicular, so we have the right angles, and we also have the reflexive property shared here. So we know that the triangles are similar, so that means we can set up proportions just like all the other ones. So if I look at the small triangle in comparison to the big triangle, small triangle is going to be, if I compare the 8, that corresponds to 20. So I'm not really using the 12 here. I only use the 12 so that I could get the 8, because you want to make sure that you're using the side of the triangle. So it's 8 to 20 is going to be equal to his height, which is 6 to the height of the tree. Cross multiply here, so we get 8 times h equals 6 times 20, so 120. Divide both sides by 8, so you get 15. So that means the height of the tree is 15 feet. It says to the nearest tenth of a foot. So that means when we round, even though it comes out to be a whole number, we have to write it as 0.0 because it's asking for the nearest tenth. So height of the tree will equal 15.0